Welcome everyone to this sixth session of Statistical Learning in Practice. In the last session, a theory session, we started a section called Model Selection and Regularization. And we spoke about model selection precisely, and today we're going to speak about regularization. So regularization as a methodology or an idea to achieve model selection, but actually it has more general purposes. Okay, so maybe let's just write down here regularization. So this should be section 1.1.54 regularization. So the general idea, let me just say it in words, and you'll find it in the PDF notes. So the general idea is that you can do something to your existing model fitting procedure, okay, so that you can sort of play around with the bias variance trade-off and achieve a better prediction error. So what do you do? Well, you take you take a model, and this, and you have a procedure to fit the model, and you're going to modify this procedure so that you introduce some regularity in the solutions, okay, some extra regularity in the solutions. What is this going to do? Well, by adding this regularity, what you are pretty much doing is actually restricting your fit of a model to a sort of smaller class of solutions, because they need to be regular. So that's an additional restriction or condition on them. And so by being restricted, then you have less variability because they can move, so to say, I'm talking intuitively in all of this, they can sort of vary a bit less than they would otherwise. So there is less variance, and because again they can vary a bit less, then the complexity of what they can model is a bit lower, so the bias will increase. And the hope is that if you modify the procedure appropriately, then actually this increase in bias will not be too bad compared to the decrease in the variance, and essentially you will achieve a better sort of total or composite error. Okay, so how does one, is there also a general idea on how to achieve this regularization, how to implement this, or how to pretty much modify the procedure that at hand? Yes, so generally speaking, the fitting procedures are optimization methods, optimization problems, right? So what you can do is to write this optimization problem as a minimization problem, and then add to this objective function, add a term that we call the penalty term, and then you try to minimize the sum of the two. Okay. So let me be a bit more specific with the GLM, and then you'll see what I mean by all of this. So, okay, so in a GLM, let me just do something. Okay, so in a GLM, so for instance, in a GLM, okay, let us let's take a function. So let L be a function from the space of the responses to the positive real values. So this is something like a loss function, but let this be, for instance, the negative. So the negative log PDF, okay, at a given point, of a point, of a data point. Okay, or we can also take the generic deviance residual. Okay. So then you'll understand now when I write the following display. So a typical regularization procedure is going to be given by the following. So this is, so we modify our, okay, so let me write it. So arg min over the betas in RP of, the sum from I equal 1 to n of this L at the yi, comma, the mean function, so the image of the linear, or the ith linear predictor. Okay, so far, if we stopped here, it would be, our original way of fitting the beta parameter, especially if we take here the negative log PDF, right? And what we can do to this term is to add this penalty term. Okay. So what is this? Well, so where lambda greater than or equal to 0 is the so-called, is the regularization parameter, or tuning parameter. Okay, and I define this beta QQ as the sum from j equal 1 to p of the kth powers, sorry, qth powers of the beta, and then q has to be non-negative. Yeah. Okay. Good. So this is for GLMs. Now, for this, for the rest of the session, we're going to focus on the linear model. So rest of session. Linear model, yeah? Because this then gives us explicit expressions for the solutions of these things for some particular cases, and it essentially returns some of the most famous regularization procedures up there. Okay, so let's introduce some notation. So we're going to change the notation slightly. So write alpha for the intercept parameter, okay, and beta for the rest of the parameters. Okay, so by this I mean that, and this without, this with some abuse of notation, right? Because we were calling beta all of the parameters, and so what we've done is just take the first element, which is the intercept, take it out, call it alpha, and then call the remaining parameters beta. So we sort of renamed beta, and so we also have to redefine the x and p. So these are also, so okay, so redefined accordingly. Yeah. What do I mean by this? Well, the design matrix, the first column was going to be all ones, so we're going to take that one out, and then the remaining matrix is x. And with P, now we've taken out one parameter. So really we have, the capital X. So the design matrix is n times P minus 1, but we're going to call this P minus 1P. Okay, so we're redefining these quantities. So two things that we do want to have on the capital X are the following. So for okay, so without loss of generality, we center the columns of X. Okay, so what does this mean? Well, it means that if we, that we modify capital X so that this happens. Okay. Okay, and this would, if anything, if you do the linear model after centering, then what you're going to change is, the value of this intercept, but it's fine, right? Because the intercept has a meaning, and the meaning is, of course, in this case, subject to, whether you performed this transformation or not. But it's fine, yeah, in itself. And then the other thing we really want is the following. So look at the definition of this beta hat above. And just imagine that you have, the usual residual sum of squares in this data fidelity term. Then what's going to happen is that this penalty term, right? So remember, is given by this quantity here. This quantity here gives exactly the same weight to each of the, sorry, and this should have a subscript of J, now that I'm looking at this. So it gives exactly, the same weight to each of the coordinates of beta, and it's multiplied by lambda, and they all are multiplied by lambda. So, lambda doesn't change with the beta. So so then this means that if they are, different entries of the capital X matrix, well, or of the columns are in different scales, very different scales, then the betas will have to adapt to this. And so if if we have if we have betas on different scales, then we will penalize a lot more the betas that are in scales that mean that the beta, the according, or the, sorry, the associated coordinate is a lot larger, yeah, because this will be penalized a lot. So really we want to have some sort of unification of or standardization of the columns of the design matrix. So without loss of generality, we center the columns of X, and we also, so we also force them, so the columns of X, to have unit variance. Okay. This mathematically can simply be written as follows. So we're assuming that the transpose of capital X times X is equal to the identity. In this case, a P by P identity. Okay, so assuming this, let's now go into, let's specialize these regularization procedures to the linear model. And so so we're going to start with the so-called lasso, and also with the rich estimators, estimation or estimators, depending on what you want to say. So estimation. Okay, so let's have a definition for these guys. So definition 5. So for all lambda greater than or equal to 0, the lasso And this LASU is actually an acronym for least absolute shrinkage and selection operator. So this will be written out in the notes. So the LASU and the ridge, in this case, regularization estimator, estimators are given by the following. So in the case of the LASU, we have, so remember we are splitting the intercept and the rest of the parameters. So this is going to be the argmin over alpha beta in the real line times this RP, and is the argmin of, in this case, we're in the linear model, so we can look at the the residual sum of squares directly. Okay, and we're going to add to this penalty term. So this is lambda as usual. Okay, and what we've done is to add the L1 norm. Yeah, so small L1 norm. Yeah. And then, so I will comment on this in a sec. And then the other, so the rich estimator that we denoted as this. So rich is the argmin, again, over the same parameter space of, the same residual sum of squares. But now the penalty term is the L2 norm squared. Okay. Okay, so let's sort of make a few comments about this. Well, this is what I was saying, right? As the residual sum of squares, or or also the negative log likelihood. So this is very related to this negative log PDF that I was talking about, right? Because you can write out this as the sum over the data points of precisely the negative, well, up to constants, but negative log PDF, or also with the deviance and residuals. Okay. In this case is, of course, the whole deviant at the moment, because we have the sum of them. And then, as I said, this is the regularization term, and same for that one, of course. So this is the regularization penalty term. Okay, yeah, that's fine. Okay, which is different in both cases. And this is the regularization parameter, right? Okay. So a few more comments. So first of all, remark. Y does not have to follow a linear model, right? So all we've done is just to modify the fitting of the linear model, but that, of course, doesn't require the Y to be, following a linear model. And also, this usual assumption is not needed. Okay, at least to write this out. Yeah. So let me now comment on this last bit. So what we're saying here is that we allow for more parameters than data points. So that's the usual sort of I guess high dimensional statistics. And what do I want to say here? Well, if we had, so let's focus on rich for a moment. If we had the residual sum of squares without the regularity parameter, then this would be essentially, well, it would be exactly the fitting of the linear model. And then, of course, the p less than or equal to n is necessary, because otherwise we just cannot find the, we just have infinite solutions otherwise. Yeah. So that term, the residual sum of squares, is convex in beta. And if we add this penalty term, then this is strictly convex, and it will strictly convexify this objective function. And what will happen is that there is a solution even for p larger than n, okay, greater than n. Yeah. So there is always, so I guess you can find this more detail in notes, but I guess for rich, I just want to say that the solution always exists and is unique. Okay. And this is why I defined this through equality. And there is a closed form solution as well, which is great, that you can find in the notes. And the situation for lasso is a bit different, because we have this convex residual sum of squares, and then we add something that is convex but it's not strictly convex. And it turns out that this is not always sufficient to get existence and uniqueness. Okay. But it is true that in most practical situations you will have existence and uniqueness, but not in all practical, relevantly or practical relevant situations you will have a closed form solution. Okay, so the closed form solution, you will have it for p less than or equal to n. Okay, situation. So that you can find in the example sheet. Yeah? I think in the second example sheet we'll see that. Okay. Okay, so fine. So this is a remark about these two estimators, and let's try to get a bit more intuition as to what each of these two guys is doing. Okay, so more intuition, so more on rich and lasso. So note that lasso and rich are Lagrange type formulations of the following constrained optimization problems. So we have the argmin again over the alpha beta combination being this product space, and this is of the residual sum of squares, of course. Okay, but now subject to the sum, well, or the norm, excuse me, of the beta being less than or equal to some t, and that's for lasso. And then for rich, what we have as the condition is this, yeah? And this is, of course, for t greater than or equal to 0. Yeah? I guess just a comment about this t is that, it is in one-to-one correspondence with the lambda, so with the regularization parameter. Okay. Of course, sort of inversely proportional there. Okay, so let's have a plot then. So what this new formulation allows us to do is really to get intuition through a plot. So let's plot and this is going to be for p equal 2. Okay. Okay, so for a given t, let's start with lasso. Well, what is the condition? And this is the beta 1 axis and beta 2 axis. So what is the condition? Well, the condition is that the L1 norm is less than or equal to t, and you can sort of check that such constraint corresponds to this shape, this geometric sort of shape. So you've got to be here. Your beta parameter has to be here. And now let's assume, just for the sake of the argument, that here is where we can place the OLS estimator. OLS. Now let's draw some. Let's look at the residual sum of squares. So this OLS is basically the minimizer of this residual sum of squares. And what we can do is to look at the contours around it. And maybe they look something like this. Okay. Okay, and if we carry on plotting these contours, which is a terrible contour in this case, okay, we'll see that if we carry on doing this, then we get here the beta. This is the first time it will hit that, so we've basically minimized the residual sum of squares, and here we'll get the beta lasso. So we can do exactly the same thing for no, it's not this one. So we can do exactly the same thing for rich. Okay. So this is beta 1, beta 2, and this is t, say. But now if we look at the constraint from the L2 norm, then of course this is just a circle. So, the solutions must be inside that. And then again, imagine we've got the beta hat here, which is the OLS, and that we try to draw the okay, so these sort of contours, then what will happen, and you can try to repeat this operation or this plot, is that essentially this is because of the because the boundaries of the constraint region are not sharp as before, then you will see that in many occasions you do not hit a point or a bit of a boundary where the parameters are exactly 0. Okay. But instead, you have, of course, compared to the OLS, we have shrunk the values, so they are smaller now, but they're not exactly equal to 0. Some of them, as beta 1 was in the ASU plot. Yeah. Okay. So let's see what we can. So what we can conclude out of this is that, zeroes out coordinates. Okay. And what it is going to do is to encourage encouraging sparsity. Yeah. Excuse my writing, sparsity. Okay. And indeed, what we know is that it will perform automatic model selection. Yeah? The other thing we know is that rich is not as aggressive. Okay. But it will shrink parameters. Yeah? And this will in turn imply some regularity, right? So, but will shrink parameter values and induce regularity. Okay. All right. So enough for lasso and rich. So let's now talk about principal component analysis. Oh, I forgot to say now. I just realized that we have seen some regularization procedures already, and that is the best submodel selection of submodel using AIC and BIC. Okay, so I'll let you think about that so you can see in the notes. So that comment is in there. And what one uses in those is actually an L0 regularization or penalty term. Yeah. And the data fidelity term is this negative log likelihood. Okay, so it is in notes, so just sort of think about this a bit. Yeah. Okay, so principal component analysis, let us recall that y hat, and by this I mean the prediction of y through OLS, which is, well, okay, maybe let's just write it as this, right? So this is going to be, I remind you, the projection of y onto the span. It's not going to fit. Onto the span of the column space of X. Okay, so first column up to the pth column. Okay, so the idea now is the following. So maybe most variability of the column space of X is within some some plane or some linear subspace okay of smaller dimension. So then the idea is to say, well, let's look at this, let's find this subspace in which most of the variability of the column space of X is contained. And let's then project the Y onto here. And so if the Y, if the variability of Y is actually aligned in some way with the variability of the column space, then that should be enough to explain most of Y. Yeah. An example in which there is an alignment between the variability of Y and the column space of X is precisely the linear model. But again, I mean, in the same way that in Rich and Lasso, I remarked that you don't need to be following the linear model to just simply apply the procedure. Well, you can do exactly the same in OLS, and there will be situations in which there isn't this alignment of the Y and the variability of the column space of X. And this will be problematic because, of course, the predictions for the Y are not going to be as good as if we had, sort of carefully designed the subspace that we're going to project it on. And this is something quite important, actually, because there is a tendency in practice, and I don't mean, of course, every practitioner, but there is a tendency to just apply these common methods without really reflecting on these kind of things. And you should reflect on these because they really have an impact on your final estimates and therefore the use that you're going to give to the methodology. Okay, so how do we find this subspace of highest variability? Well, let's focus on, so let P be less than or equal to n, okay, for this section. And by the singular value decomposition of X, we have that X can be written as the product of three matrices. So this is capital U, capital D, and capital V transposed, where we have that the U is an n times p real valued matrix, such that it satisfies this. Then D is a diagonal matrix, or well, maybe let's say this is an RP times P is a diagonal matrix, such that the first element is greater than or equal to the second element of the diagonal. So this just means that we assume they are ordered in decreasing order, and they are non-negative. Okay, so that's an assumption. Well, it's not an assumption, but it's a conclusion. I think that's something that happens with this capital X. Okay. And then the last thing is that the V is unitary. It's a unitary matrix, yeah. So what can we say about this now? Well, then let's look at this variability that we were talking about. So for all W in RP, we note that maybe, so let's say note that for all vector in RP, the variance the variance of this linear combination of the columns of X, and here we're going to use the fact that the columns of X are centered, so it's going to be given by this just this quantity, yeah, right. I mean, that's clear because we use the fact that X is centered. And if we write it out with the singular value decomposition expression that we have in there, then we can, we can conclude, or we conclude that this equals the following expression. Okay. And what this means is that, so if this W equals, the ith, or actually probably the jth, let's see, excuse me, yeah, so the jth column, then the right hand side is going to be equal to this, right? And that should be clear, yeah, because we have that the V is a unitary matrix, yeah. So if this, then this happens, yeah. And in particular, so this means that the variance, okay, so this also means, okay, let me just, sorry, I keep getting prompted by an app or something. I'm getting very distracted now. Okay, so okay, so if this happens, and the variance of xw, which, by the way, we can write as follows. So we can write it as the sum of a j, or from j equal 1 to p of the djj squared, and then the v, so the jth column, okay, times the w squared. Okay, so we have this sum of non-negative terms. So this is maximized over the set of vectors that have norm 1, okay, which, by the way, if the w has norm 1, then it means that this no, actually not that, but rather the v here. So this has norm 1 as well. Okay. And so if this has norm 1, then what happens is that these guys are going to be, they're going to be adding up to adding up to 1. And so, of course, if we wish to maximize this over this set of vectors, then what we want is to have all zeros except for the first entry that we want it to be exactly 1, yeah, because then we'll have achieved the maximum of this. So this is maximized over that by w being the first column. Okay. Okay, so by similar reasoning, by the same reasoning, if we wish to maximize the variance of this guy over the set of vectors that are unitary and such that w is orthogonal. So remember, we're looking for a subspace, right, that has the highest variability. So once we get, a vector for, the highest variability direction, then we want another direction, and we can perfectly wish it to be orthogonal, because that's the usual way of creating a basis, and in fact orthonormal. So then if we wish to maximize this over this condition and such that this is orthogonal, then W should be the second column of B, okay? And so on, yeah? And so on. As in, you see that the columns of the V are the ones that are going to be having highest variability without with these conditions here, yeah? Okay, so then just for terminology, then djj times U, not V now, but U, so the jth column, which is, by the way, equal to precisely the xv at the jth entry. Actually, well, this is not a vector, but rather a matrix. So I mean the column, the jth column, which is, by the way, just x times the jth column of the V. Then, and this is due to, of course, okay, due to xv being equal to du. Okay, then this guy is called the jth principal component. Yeah. Okay, so to predict y, it is common to regress it only on the first j principal component and normalized. Remember, we said we want some basis orthonormal. So the first j normalized principal components. Okay, where the j is defined as the, and j must be less than or equal to p, is the first natural number such that we have the ratio of the variances. Okay, so the variances up to j, or the proportion that they represent in the total variance, is greater than or equal to, say 80% or 90% or 95% typically. Yeah, so these are typical values depending on the application at hand. So there were a few more things I wanted to say, but I'm not going to have time now to say, to state them. So I will include them in the notes, and then we can, it's a comparison between OLS, RIDGE, and LASSO, and essentially the conclusions are that RIDGE indeed, so firstly, that they are very related, the three of them, and PCA, sorry, as well, and the RIDGE is going to perform better than OLS, and then that LASSO is going to do correct model selection. So not only automatic model selection, but also a correct one. And it will essentially behave sort of nearly as an estimator that knows what the true model, I'm talking about the linear model, of course, assuming the linear model. So it will act as or perform as what is called the oracle estimator, which knows what submodel is giving rise to the data. Yeah? And this is without even knowing whether there is a submodel giving rise to the data or just the whole model giving rise to the data. Right. Well, thank you for your attention, and I'll see you this week at the end of the week, so Friday, and later on in the office hour. Thank you.